Thank you. Thanks for coming today. We're going to talk about the microcode downgrade and a few words about me. Mostly I do firmware security research, and my favorite subject is Intel ME, UEFI BIOS, and technologies hardware-based like Intel BootGuard. Today we will be going a bit down into the hardware and talking about the microcode basics, about the microcode downgrade technique I've discovered, and then we'll talk about the impact. So let's start with the microcode basics. If we look at this inside the Intel CPU, we will see that it has a few cores, like each modern CPU. The main core is called bootstrap processor. It is the core which starts executing the code when CPU is powered on and released from the reset state. The application processors are the other cores which are to be woken up by the bootstrap processor when some conditions are satisfied already. Also, CPU can have graphics core, memory controller, shared cache level 3, and some input-output logic. Each core has its own control units and arithmetical units to perform to decode instructions and perform arithmetic operations. Also, each core has a register file and caches, level 1 and level 2. So what is the microcode actually? It is a program inside the read-only memory, which is stored inside the CPU. Each core has its own read-only memory. It is not updatable, but to execute the microcode, it is being loaded into some kind of SRAM, which called control store usually. As you can see, the microcode usually implements instructions like this one in the more basic language, in the more basic instructions for the CPU. So, as we have already found out, CPU and the microcode can contain vulnerabilities, so it should be updatable. Like I already said, it is stored in the read-only memory, which is not updatable, not modifiable at all. But to update the microcode, it has to be loaded in the control store each time after power up. To do that, there is a firmware interface table, which I've mentioned in this slide here. The highlighted entries in this table points to the microcode updates for different CPUs. You can see that the CPU ID is different for each entry. A few words about this firmware interface table. It is a part of firmware image. It's stored in the BIOS region, and its pointer is located at this address in the memory when the SPI flash image is mapped into the memory of the CPU. So that's how CPU can find this table and to load microcode updates automatically. Since introducing the Intel BootGuard technology, firmware interface table is a required element. As we can see, it can point to microcode update binaries, and CPU can automatically load microcode updates from firmware interface table, and this is done before the execution of the BIOS. if you look at the microcode update binary file, we can see two headers. First one is the main header. It has some usual fields like sizes, versions, and the most important for us here field is the processor signature field, which says the CPU ID of the processor for what this microcode update is intended to be applied. And the other field is update revision. This field is like a version of the microcode. So you can retrieve this revision from one of MSRs and says which update is loaded into the CPU now. The second header is the extended header, which contains some sizes and versions fields also, but the most important here is the signature. It contains RSA public key and signature that allows the CPU to authenticate the microcode update, this microcode update, before loading it, and that's why you cannot just simply modify the update. This is one of the reasons why you can't modify the update. The second reason is because the update data is stored in an encrypted format, and the key to decrypt is stored inside the CPU. So only the CPU can decrypt the microcode update, and also the CPU can authenticate the microcode update before loading. These are the reasons why no one can modify the update, and that's why, because no one exactly knows what microcode is capable of, because it is encrypted. However, there are some known facts about microcode. It implements instructions. Like I said before, it should configure the execution logic on the line, and that's how the famous side channel vulnerabilities are fixed. It implements some startup behavior, like firmware interface table parsing, like I've mentioned before. It also can load microcode updates from firmware interface table, and one of the important things is the capability of loading Intel authenticated code models from firmware interface table or not. A few words about these models. The ACMs, authenticated code models, these are signed, and sometimes for some technologies these are encrypted blobs provided by Intel into firmware. Usually they serve as a root of trust for such technologies like Intel Boot Guard, Intel BIOS Guard, and trusted execution technology. The Boot Guard is a hardware-based verification technology for the BIOS. It allows to authenticate the BIOS before executing it by loading the ACM. So microcode loads the ACM, which verifies the BIOS, and then if the verification was successful, the BIOS is allowed to be executed. The next technology is the BIOS Guard. It's formerly known as PFAT, Platform Flash Armoring Technology. The main thing is that this technology allows to lock the SPF flash write access to the ACM, the BIOS Guard ACM, and if this technology is enabled, only this ACM is capable of writing onto SPF flash memory. That's why how attack surface is reduced to the small blob, which is encrypted and signed by Intel. And the latter here is trusted execution technology, which allows to measure trusted boot chain components during runtime using the trusted platform model, TPM. It is also based on different types of ACMs, like CNIT ACM and BIOS ACM. Here are a few links to start digging if you're interested in this subject. You can read something about the microcode here. So let's go to the downgrading technique. First of all, I've done some reverse engineering on the microcode loader implemented in BIOS, and here are a few thoughts I've discovered. First of all, updates are to improve stability, performance, and apply security fixes. That's why they are important, and usually if there's no microcode update, the platform won't even run, won't even power on. Also, updates should be loaded each time CPU is powered on. This literally means leaving the sleep, hibernation, and shutdown modes every time CPU is powered on. Each core has its own microcode, like I've said before, so the microcode update should be loaded onto each core of the processor. Also, the most important thing I've discovered that far not always the microcode updates could be loaded by CPU automatically from the firmware interface table. I don't know why all the cases when it is not happening, but the most spreaded case is some updates require have special requirements for example, for initialized memory. So they cannot be loaded before memory is initialized, and the BIOS has to done it manually after the conditions are satisfied. And that is the most spreaded case for us. And this is the point why the downgrading is possible, actually. So the loading process looks like this. It is it could be implemented via MSRs. There are MSR to trigger the update process. You just need to point the linear address of the update and trigger the update itself. Also, you can check the microcode update, the revision that it was actually applied via reading the MSR, the other MSR mentioned here. It will return in the RDX register the revision ID of the update. Let's talk about the loader implemented in the BIOS. The first steps when the normal boot occurs is performed in the CPU-V model. It finds the appropriate and non-applied update in the firmware interface table. Then it copies it from the SPI flash memory into a buffer allocated in memory, and saves the pointer to this buffer into a handoff block. This is some structure in memory, it doesn't matter. So later, this handoff block is retrieved by platform init model and parsed. The address of the stored in-memory microcode update is retrieved, and then the update loader does the thing. It updates the microcode with the pointed update, and that's all. But here are a few steps done in system management mode later upon normal boot. First of all, this CPU SPSMI model finds the same handoff block and retrieves an address of a loaded microcode update. It copies it into the system management RAM. It is a closed memory close to operating system I think this is done for the purpose of protecting the microcode update from modifying by code, by software from operating system. And the pointer in SMRAM of this update is saved into the variable, into EFI variable called int microcode, int ucode, as you can see here. The question is why these sections are performed in the end, and the answer is an optimization while waking from sleep mode. So if we, after waking from sleep mode, if we go to CPU P model, we can see that it doesn't search for the microcode update in the firmware interface table. Instead, it loads the saved address from the int ucode variable and applies and save this address into a handle block, and then platform unit model can does the same thing it does upon normal boot. It loads the provided microcode update, and that's all. This specific allows to do some actions by an attacker. Like an attacker can loot a null microcode update somewhere in the memory. He can make the int microcode variable to point into this block of memory and perform sleep wake up cycle. That's how microcode could be downgraded to the version provided by an attacker. I should mention that the system will be booted with this microcode, with the provided microcode, only if it was valid and passed the integrity check. However, the downgrade is possible that way. So as you can see here on the same CPU, I've managed to downgrade through the sleep wake up cycle from 2019 version of the microcode to some version which was built in 2018. Let's talk about the impact of this technique. First of all, the first thing that comes to my mind is the side channel attacks, the famous side channel attacks that were fixed in the microcode, like Spectre, the second variant. So this technique allows to downgrade the microcode to an unfixed version and to get rid of the patches for side channel, for some types of side channel attacks. I should mention that most of them are extremely hard to apply in the wild. However, and they have never been spotted, but there's not much of detection tools. I've mentioned one that I've managed to find. And also, if you would like to know better about the side channel attacks, you can read this paper by Alexander Rumyantsev. It describes all these side channel attacks in quite interesting way. The second thing, the second consequence of the downgrading the microcode is unlocking debug capabilities. The thing is, I've discovered that some debug capabilities was patched in the microcode. So if you will manage to downgrade them, you will be able to use such technologies as Intel DCI. The most interesting thing is I've discovered is that the ACMs could be also downgraded via the microcode downgrade. The reason they can be downgraded is that the old microcode allows to load old ACMs with the downgraded, reduced security version number in version. This is possible because the ACM authentication is performed by microcode. So it allows to exploit 1 days and influence the technologies that are supported by ACM. These are bootguard, BIOSguard, and Intel TXT. So let's talk about the bootguard ACM. It is not encrypted. You can easily find 1 days in it by applying a binary diffing. It is executed only on startup before the BIOS, like I've mentioned before. And the thing is that this ACM does not verify BIOS when waking from sleep because of performance optimizations and except each 12 boot. That's why the downgrading and downgrading the microcode and this ACM is not necessary because when waking from S3, there's no verification actually. So let's talk about the BIOSguard. The BIOSguard ACM is encrypted and it is extremely hard to find a fixed issue in it. So it can be triggered by running SPI flash operations through CPU MSRs. The downgrade is possible if you will manage to gain an SPI flash write access, which is also unnecessary, and because if you will gain this SPI flash write access, you are at this moment already bypass the BIOSguard, and that's why you will. There's the point to attack only the implementation of BIOSguard. The first bypass of the Intel BIOSguard technology is also in public. You can read this work by Alex Matrosov. The third types of ACMs are TXT ACMs. They are not encrypted. The patched issues in these ACMs could be found by binary diffing. There are also a few advisories and a few known public issues in ACMs. So the general target here is a CNIT ACM that performs some measurement of trusted boot components. This ACM is triggered by get_sec instruction of the CPU, and the thing is that address of this ACM in memory is provided by its caller. And it is always stored at the same place in memory. That's why you can just replace this ACM in memory, then downgrade the microcode, and downgraded microcode after waking from sleep state will loot this vulnerable ACM, and that's how we can exploit a fixed issue in these. So the problem, this is a supply chain problem. I've reported to Intel about a year ago, and it took a long time for implementing fixes for it, for mitigations. So let's talk about the mitigations. The most frequent mitigation I was heard about is Intel SJX technology. However, our experiments showed that this technology does not check the microcode security version number when leaving sleep mode, so it doesn't work for this issue. The applied The applied mitigations by American Megatrends, the bias vendor, was to protect the int microcode variable from modifying and even accessing by an attacker from an operating system. However, this could be bypassed if an attacker manages to run arbitrary code in system management mode. This will allow to gain SPI flash write access, where you can just swap the environment region and again exploit this issue. Also, one of the obvious mitigation is to make an operating system to update the microcode to the latest version. However, as you can see, the trusted boot chain can be compromised at the moment of executing the operating system. That's why you cannot trust the update provided in such a way, and the most hardening fix is for Intel to supply only the updates that can be loaded by the firmware from the firmware interface table automatically by the CPU. This will not allow to downgrade the microcode, because the downgrading to the version with the decreased update revision when the update is already loaded is not possible. So let's see a few takeaways from this problem. This is a supply chain problem, as was mentioned before. The problem exists in a basic component, and we saw how it influences and compromises all technologies it serves as a root of trust. As we don't know what microcode is capable of, the full impact is yet to discover, because it is yet unknown. So that's all for now. Thank you. Thank you. Is there any questions from the floor or?
Do we have any live questions? All right, if not, we'll move to Slido.
Is security a reason not to open source the microcode architecture? If I can install a microcode update, I've already won. Yes, you already won. I think not to open source. This is the question that should be asked. That should be referred to Intel. I guess I think the intellectual property is the reason why Intel is not open sourcing the microcode. AMD or Intel. The talk was related to Intel, the whole talk. Which has better microarchitecture security in your opinion? I think both of these companies have pros and cons. Would it be possible to use this kind of downgrading of the microcode to persist malware? I think yes. The reason is the main target of downgrading microcode is to bypassing trusted boot chain by influencing the trusted execution technology. That's the main target of persisting the malware in the system. What kind of access does an attacker need to downgrade? the microcode. I forgot to mention it. It can be done from a user space of the operating system. You just need to load the update into memory. So this can be done through any driver like RV, RW, everything, or something like that. And then you have to modify the EFI variable. This can be done from the user space of the operating system. There is a function in Windows API. I don't remember, the set firmware environment variable X. This function allowed to modify the EFI variable, and then you can. You just need to perform a sleep wake up cycle, which can be done also from the operating system. Is there a chance that certain agencies have already known about such vulnerabilities before researchers officially discover and publish? Oh, I don't really know. It's hard for me to understand this. How can we detect such attacks? I think it's possible to somehow store the security version number of the microcode somewhere in the safe place. For example, using the TPM seal functions, and if it was changed, you cannot trust the system. Has there been official instances of such exploits being used in the case of achieving certain political goals? I don't know about that. I don't know. The political subjects are hard, and intelligences and agencies are hard for me to understand. I don't know about it. So if this is all, I would like to thank you again for coming today. Thank you.